Imagine flying toward your destination, expecting a routine arrival, only to have the pilot suddenly throttle up and abort the landing. There is no violent storm in your path and no hurricane winds. The problem is that horizontal visibility has suddenly dropped to less than 5/8 of a mile. You are looking at a cloud that happens to be touching the Earth. Fog is exactly the same physical substance as the white formations floating miles above our heads, formed by the exact same atmospheric trigger. This diagram illustrates what meteorologists call the dewpoint spread. It tracks the critical gap between the actual temperature of the air and its dew point. As the air cools and that gap shrinks to within about 4 degrees Fahrenheit, the environment approaches absolute saturation. At this precise convergence, water vapor has nowhere else to go. The invisible gaseous molecules hanging in the air are forced to condense, rapidly materializing into a dense suspended matrix of tiny liquid droplets or ice crystals. To anticipate exactly when clear air will turn into an opaque wall, we have to look at the 2 specific thermodynamic paths the atmosphere uses to close this temperature-moisture gap. The first path to closing the spread is straightforward. Cool the air from the bottom up until it hits that saturation threshold. On calm, clear nights, the ground quickly radiates its stored heat out into space. As the Earth's surface chills, it cools the stagnant layer of air directly above it right down to the dew point, producing a dense, shallow layer known as radiation fog. If you add light winds and horizontal movement to the mix, you get advection fog. This requires a large mass of moist air to drift directly over a surface that is already significantly colder. You can see this process in action along the coast. Warm, moist air from the open ocean moves continuously over a frigid coastal current. The air mass cools from the bottom up, instantly reaching saturation as it blankets the shoreline. The terrain itself can also trigger this temperature drop. When wind pushes a moist air mass toward a mountain range, the air has no choice but to travel upward along the incline. This animation shows the mechanics of upslope fog. As an invisible air parcel is forced higher, surrounding atmospheric pressure decreases. The parcel physically expands, forcing its internal temperature to drop, a process called adiabatic cooling. Once it cools to the dew point, it saturates. Whether it's the cold ground freezing a stagnant layer of air, an ocean current chilling a sea breeze, or a mountain slope forcing wind into the upper atmosphere, dropping the temperature is a highly effective way to blind a runway. The second path to achieving saturation doesn't rely on dropping the temperature. Instead, it forcefully injects moisture into the air until the environment simply cannot hold anymore. Look at this offshore lighthouse. Brutally cold winter air is moving over a relatively warm body of water. That warm water evaporates intensely into the freezing air directly above it, immediately condensing to create the rising wisps of steam fog, also known as Arctic sea smoke. A similar injection of moisture happens on a massive scale ahead of weather fronts. When a warm front pushes in, rain falls into the colder, stable air mass lingering near the surface. That rain evaporates as it falls, steadily raising the dew point of the cold air until the entire zone saturates into widespread frontal fog. If you take these exact same physical processes, cooling the air or injecting it with moisture, and move them thousands of feet off the ground, you get high-altitude clouds. Once a cloud begins to form, its final shape and the turbulence hiding inside it are dictated entirely by the atmosphere's internal stability. This comparison illustrates air parcels after saturation. On the left, stable rising air is cooler than its surroundings. It stops lifting, spreading into flat stratus layers. On the right, unstable saturated air remains warmer. It accelerates upward in a violent updraft, building towering cumulonimbus clouds. A cloud's physical silhouette is a direct visual readout of the thermal energy and stability of the sky. Because these formations are bound by strict physical rules, they are highly predictable. They are the inevitable byproducts of macro-level weather systems tracking across the globe. A high-pressure system stalling over a region with clear skies and wet ground is a mathematical guarantee of nighttime radiation fog. Likewise, a slow-moving warm front practically ensures days of widespread precipitation-induced frontal fog. Aviators track these exact thermodynamic battles to anticipate severe visibility restrictions. They read the state of the sky through specialized weather reports known as METARs. This grid breaks down how aviation reports measure cloud coverage. The sky is divided into eighths, called octas. Few means 1 to 2/8 of the sky is covered. Scattered covers 3 to 4. Broken hits 5 to 7. And overcast means absolute, 8/8 total obscuration. When it comes to visibility on the ground, the terminology is just as strict. If suspended water droplets restrict your horizontal vision to 7 miles down to 5/8 of a mile, it is reported as mist. The second visibility drops below that 5/8 threshold, it is officially classified as fog. By tracking the mathematical spread between temperature and dew point, we can read the sky like an aviator, anticipating exactly how and when invisible moisture will materialize into an impenetrable wall of white.